Welcome back, everyone, to section number 3. Again, this is the fundamental theorem of calculus. Here we are in part 2. In this video, right, we're going to state the second part of the fundamental theorem of calculus, and the claim is this is the one that we really want. We're going to go over the idea of the proof, kind of similar to the last video, and then we're going to do some examples, right? We're actually going to use this to calculate out some definite integrals. Okay, so the first thing, what does the second part of the fundamental theorem of calculus say? So if we have a nice continuous function on an interval from a to b, and we'd like to get its definite integral, right? The integral from a to b of f of x dx, the claim is this is going to be equal to capital F of b minus capital F of a, where capital F is any antiderivative. Remember, this was some terminology that we brought up at the very end of chapter number 3. An antiderivative of f, that is that when you take the derivative of it, you get back to where you started. You get little f. And oh my goodness, this is going to make our definite integrals so much faster. I'm excited to do it. Let's first talk about the idea of the proof, right? Why does this work? How are these definite integrals and antiderivatives related? I actually kind of talked way at the beginning of this chapter that, right, actually the area under the curve has something to do with derivatives. And more specifically, it has to do with the antiderivative. And so again, this left-hand side, this definite integral is area under a curve, right, from a to b. And this right-hand side is an antiderivative. So again, it's kind of alarming maybe that these are related. So here is the idea of the proof. I'm going to go ahead and consider f of u, which I'm going to define by the integral from a to u of f of x dx. So this is very similar to what we have up here, except for I'm having this u be a variable instead of b, right? B is some constant, u is going to be some variable. And we actually know that this capital F function, f of u, is an antiderivative of f of x. And like I said, this is going to rely, the second part of the fundamental theorem of calculus relies on the first part. And the reason why it's an antiderivative is because of the first part of the fundamental theorem of calculus. So this is by the first part of the fundamental theorem of calculus, right? So if you take the derivative of this, you get back to where you started. So that's why we needed this fundamental theorem of calculus, the first part. So the most general antiderivative of f is given by f of u plus some constant of integration. Again, think back to our the very end of chapter 3, 3.9. So in this case, I want to know which antiderivative do I want. So I'm going to go ahead and consider the integral from a to u of f of x dx. Well, again, this is going to be equal to some f of u plus a constant of integration. That's the most general one. And if I was to go ahead and plug in maybe a everywhere I see a u, so this is going to be the integral from a to a of f of x dx, and that's going to be f of a plus c. Again, plugging in an a everywhere I see a u. Well, why do I do this? It's because now this left-hand side is equal to 0, right? We want the area under the curve from a to a. Well, there is no width behind this, right? So therefore, this must be equal to 0. And this allows us to solve for our c value. This is saying that c has to be equal to negative f of a. So this is now specifying which antiderivative I want, right? Because there are infinitely many of them, plus any old c, and I have to figure out which antiderivative is the correct one. So I found that when c is equal to negative capital F of a, that is the correct one. So in this case, we have that this integral from a to u of f of x dx is going to be equal to f of u minus f of a. And so the last thing, right, my goal was to get a way to express this integral from a to b. And I've been using the variable u for a while now. So let's go ahead and plug in a b everywhere we see a u. So plugging in b for our variable u, we get that the integral from a to b of f of x dx is equal to f of b minus f of a. Again, plugging in b everywhere we see a u. And that is exactly what we wanted to prove. So that is the fundamental theorem of calculus part 2. And really kind of combining these two together, the fundamental theorem of calculus really state that differentiation and integration are inverse processes. Right? They undo each other, right? If you take the derivative and then the integral, they kind of undo each other. If you take the integral and then the derivative, they undo each other. It's like addition and subtraction or multiplication, division, right? They kind of undo each other. And right, from our perspective, the fundamental theorem of calculus part 2 is really our favorite because it's going to allow us to calculate out these definite integrals much, much faster, right? We won't have to do this limit as n goes to infinity of these horrible sums, right, from all of the areas of rectangles and stuff. So this is going to be much, much nicer. Let's see how it's done with a few examples here. So I want to evaluate out the following integrals. And really quick, there's some nice notation here. This f of b minus f of a, where we're talking about an antiderivative. This can be also denoted by this capital F of x as we evaluate from a to b. Or likewise, you can use kind of big brackets here from a to b. So this subscript and superscript, right, this is another way to say I'm going to plug in b, and then I'm going to subtract away plugging in a. Right, so we'll use this notation. This is going to become very convenient. You'll see why here in just 1 second. All right, so let's do 3 problems here. This first one, I want to figure out the area under the square root function from 1 to 9. Well, another way to write this, right, is that I want to do the definite integral from 1 to 9 of x to the 1/2 power dx. And from this fundamental theorem of calculus part 2, we know that this has something to do with the antiderivative. So let's go ahead and try to calculate out the antiderivative of x to the 1/2. Well, this is going to be like an x to the 3/2, and then I'm going to need a 2/3 right here. And let's double check. If I take the derivative of this, do I get back to where I started, right? So the 3/2 would come down and cancel with the 2/3, good. And then I'd reduce my power by 1, so I'd go from 3/2 down to 1/2. Excellent. So this is an antiderivative, and according to the fundamental theorem of calculus, this is going to be equal to an f of b minus an f of a. So I need to plug in 9 and 1. So I'm going to go ahead and use this notation here and say that I'm going to plug in 9 and then 1. And so let's go ahead and do that. So I'm going to have 2/3, and when I plug in 9 into the 3/2 power. So, okay, remember, you have to cube this and you have to raise it to the 1/2 power, but really the order is up to you. So if I raise it to the 1/2 power first, right, 9 to the 1/2 power, that's the same thing as the square root of 9. That's going to be 3. Now, if I take that and I cube it, right, so 3 cubed, that's going to be 27. So again, I took 9 and I raised it to the 1/2 power and the 3rd power, but again, the order is really up to you. And then minus, if I take 1 and I have to again cube that and raise it to the 1/2 power, the order is up to you. Kind of any order will give you 1 here in this case. And so our final answer is going to be 2/3 times 26, and that's going to be equal to maybe 52 divided by 3. And so again, maybe because this is our first example, let's go ahead and visualize what we've done here and verify our work. So I went ahead and pulled up a quick Desmos graph here. I did f of x is equal to the square root of x, and then I did the shading, right? So I did the shading from 0 up to our function when x roams between 1 and 9. And so there's a cool thing you can do here, right? If you do int, right? And this will allow you to do the definite integral. And I'm going to do from 1 to 9 of our f of x dx, and then this is equal to 17.33333, right? So it'll calculate that out for us. And let's go ahead and verify our work. We thought that the answer was, what, 52/3. So if I go ahead and calculate 52/3, again, 17.33333. So we were actually able to calculate out this definite integral using antiderivatives, right? And so this is very powerful. This will allow us to not have to use these limits and the sums and all that sort of stuff. So I'm very excited about this. So again, our answer is 52/3, and this is a nice way that we can go ahead and check our work. All right, for our second example here, okay, so I need to take the antiderivative of this function right here. I remember there was a product rule for derivatives, but I don't remember a product rule for antiderivatives. So, okay, there is no product rule for antiderivatives, so in order to solve this, we're going to go ahead and do some simplification first. I'm going to go ahead and distribute all of these pieces. So again, from -1 to 5, and I'm going to FOIL this out. So firsts, let's see, inners would be u, outers would be -2u, lasts would be -2. And so this can be simplified down to the integral from -1 to 5 of u squared minus u minus 2 du. Okay, so according to the fundamental theorem of calculus, well, I need to find an antiderivative, and then I'll take that antiderivative and I'll evaluate from -1 to 5. So, okay, the antiderivative of u squared, I think this is going to be like u cubed, and then times 1/3. Let's double check. If I take the derivative here, do I get back to where I started? Absolutely. Negative, and then maybe like u squared and a 1/2 out in front. Again, the negative's kind of along for the ride here. If I take the derivative of u squared, that 2 will come down and cancel with a 1/2. I'll reduce my power by 1, and so I'll get u to the first power. So yes, this works out. I have now these two. And the derivative of something to give me -2. I think this is going to be -2u. Again, double check. If I take the derivative, I get back to where I started. Excellent. So now let's go ahead and plug in our f of b, so that's 5. So I'm going to plug in a 5 everywhere I see a u. So that's going to give me 1/3. 5 cubed is going to be 125 minus a half. 5 squared is going to be 25 minus, okay, 2 times 5, that's going to be 10. And then subtract away when I plug in -1. So when I plug in -1, -1 cubed is going to be -1. So I'm going to have -1/3. Let's see, -1 squared is just going to be 1. So that's going to be minus a half. And then when I plug in -1 here, this is going to be +2. And now in order to simplify this, I like to group together kind of the common terms here. So these two both have division by 3. And these two both have division by 2. And then here we have division by 1, right? So these are just integers. So I like to kind of group these things together. I think it usually makes life a little bit nicer. So I'm going to have, let's see, 125 thirds. And then I'm going to subtract away -1/3. So that's going to be the same thing as adding 1/3. Okay, I'm going to have -25 halves. And then I'm going to subtract away another -1/2. So that's going to be the same thing as adding a half. And then finally I'm going to have -10, and then I'm going to subtract away 2. So this is going to be 126 thirds. Let's see, minus 24 halves minus 12. So 126 thirds. Well, this may take a minute, but that's going to be equal to 42. Minus 24 halves, well, that's going to be equal to 12, minus another 12. So altogether, I believe that we get 18. So there is our final result. All right, and again, just for fun, let's go ahead and check our answer. So I went ahead and I graphed this u plus 1 times u minus 2. U plus 1 times u minus 2, and then I went ahead and I shaded. Remember that if it's below the x-axis, this area gets counted negatively, and if it's above the x-axis, then the area gets counted positively. So I did the different colors for the different shading here. And then let's go ahead and evaluate out. Again, I'm going to use int for integral, and then we're going to evaluate from -1 to 5 of our function f of u du. And this is equal to 18. And so what this is telling us right here is that if we were to add together all of the area, all of the red area and all of the green area, right, that the green area beats out the red area by 18 units, right? So there's more above the x-axis or u-axis than there is below. And how much more? Well, there's 18 more. All right, so that is our second example. Verified our answer of 18. We have one more example. Let's go ahead and see if you can do this. Pause the video, try it for a minute or so, get as far as you can. My hint to you is remember there is no quotient rule for antiderivatives. So again, there's no quotient rule for antiderivatives. Try this one on your own, see how far you can get, and then unpause the video and I'll show you the answer. All right, so here's my work. Let's go over this step by step. So again, there's no quotient rule, so I need to go ahead and simplify. So similar to how I did in the previous example, how I FOILed this all out, I'm going to go ahead and distribute my division by x squared. So x to the fourth divided by x squared, well, that's going to be x squared, and 1 divided by x squared, well, that's just going to be 1 divided by x squared. I can go ahead and rewrite this as x to the negative second power, kind of getting ready for this power rule, right, for antiderivatives. So if I want the antiderivative of this, I think I'm going to have x cubed, and I'm going to need this 1/3. So if you take the derivative of this, do you get back to where you started? Absolutely. How about here, right? We're going to raise our power by 1, so from -2 to -1, and then we're going to multiply by the reciprocal of that new exponent here, so that's going to be negative. And double check, if you take the derivative of this -1 will come down, cancel with that negative, and then you'll reduce your power by 1, so you'll go from -1 to -2. Excellent. Now at this point, I would even rewrite this, right? Because when you have a negative exponent, this is really like secret division, so I'm going to go ahead and rewrite this as division by x to the first power. And now I'm going to go ahead and plug in these values. Remember, we're evaluating from 1 to 2 in this case. So if I plug in 2 everywhere I see an x, well, 2 cubed will be 8, 1/2 will be 1/2. And if I plug in a 1 everywhere I see an x, I'll get 1/3 and -1. So this is my f of b minus f of a. And now we go ahead and maybe simplify, and again, I'm kind of combining all of the like terms here, so these are ones that have division by 3, and then, well, there's division by 2, and this one doesn't really match at all, so okay, so these ones are kind of different, but we'll be able to combine these all. So let's see, division by 3, so we have 8/3, and then we have minus 1/3. Okay, minus a half, and then minus a -1, so that's going to be +1. And then I go ahead and write 8/3 minus 1/3, that's going to be my 7/3. And then -1/2 plus 1, I went ahead and combined these into +1/2. And then I got a common denominator, and my final answer was 17/6. Again, you can go ahead and graph this using the nice Desmos application and verify your work. But at a certain point, right, on quizzes and exams, we're not going to be able to verify. So we're just going to have to be confident in this. So it's a good idea, right? We want to gain some confidence in our work. And so you have to wean yourself off this, always being able to check, because again, quizzes and exams, we don't get this. All right, that's it for this video, and that's it for the fundamental theorem of calculus. I'll see you guys next time.